So I'm going to give an overview of the program, and we've got 4 talks later during the day that will give a bit more detail. So I'm not going to steal their thunder, so they don't need to worry that I'm going to talk about this stuff. First of all, what is uncertainty quantification? So that's my definition. Apologies to probably everyone else on the program who has a different definition. So uncertainty quantification, the estimation and management of error, and I've put that in quotes because we might discuss what we mean by error, in the use of a computer code to simulate a real-world system. So we might want to model the flow of water underground from some pollutants through underground to some well, and we use a computer model to actually simulate that. The computer model isn't the same as the equations we're trying to solve, and the equations we're trying to solve aren't the same as the real world. So what error do we get from using a computer model with uncertain inputs to get our results of how long it takes for the pollutant to get to the well? So the errors come from uncertain inputs. We don't know exactly what the structure of the rock that the water is flowing through. And there are approximations used to go from the mathematics to the computer code. We have a set of equations that describe how the water flows through the porous medium. But we have to approximate that to put it into the computer. We can't solve it analytically. So there's a discretization that's going on, and that induces error. And it might be our mathematical formulation is itself not exact. The real world isn't a set of equations, it's something much more complex than that, and there's a difference between those two, and that brings in the idea of inverse modeling, where we have some data and we try to infer something about our model, whether that's the equations or our computer code, from measurements we have taken in the real world. So those are the sorts of problems we've been looking at. And historically, 2 communities have studied these sorts of problems. And 2 communities that came at this from very different ways and came at it completely separately. 2 independent communities that really haven't talked that much. So there's the applied mathematics numerical analysis community and the statistics community. And both approach this problem from very different perspectives, or these problems. I'll say these problems because you'll see in a minute they're not exactly the same. And the program aim, which is taken from the website, was to bring together the applied mathematicians, numerical analysts, and statisticians to formulate a common mathematical foundation. Are we doing the same thing? Are we doing different things? Can we build some rigorous grand theory of uncertainty quantification? And to establish interactions between those 2 communities that don't talk to each other or haven't talked to each other in the past as much as they should, and to lead to significant advances in both the theory and practice of uncertainty quantification. That sounds very grand. We've almost got to the end of the 6-month program. So the organizers were Catherine Powell, who has done all the work, but unfortunately is unwell, so can't be here today. Max is speaking straight after me, I think. Henry, who's chairing the session, and myself. Catherine and Max come from that applied maths numerical analysis community. Henry and I are statisticians. So how many people have been through the doors? Well, we've had about 100 participants, slightly less than 100 participants. All things, there's some slight uncertainty about the number of participants we've got. I've got the official list, and I'm still not exactly sure how many participants we've had. The average length of stay was 29 days. So generally people came for just about a month. I think it's a bit skewed by Catherine and Nico and Henry staying for those 6 months. But the average time was about a month. About half of the people, when I went through and allocated people to statistics and applied maths, about half was from statistics and about half from that applied maths, numerical analysis. Some people would claim to be from both. Some people might even claim to be from neither, but and we've had really good interactions and discussions. There's been a lot of talking around tables. We've had seminars that are booked to last an hour, and 2.5 hours later we stumble out and go to lunch. So lots of talking, lots of discussion, lots of breaking down of barriers. We held 4 workshops. We got a lot more people through the doors in those workshops. 100 participants are the people who came for a significant length of time. A lot of people only came for these 1-week workshops. First one was an introductory workshop in pretty much the first week of the program. And then we had 3 more focused ones, one on surrogate models, one on reducing dimensions, and one on inverse problems. And we have done 2 open for business days. This is the second one. And the first one in February was taming uncertainty in mathematical models used in the private and public sectors. It's probably not my place to say this, but I thought the workshops were great and they were very successful. Before we started, we set out some themes, which were in the proposal. And our themes were surrogate models. Both communities use surrogate models, simple models, as replacements for big, complex computer codes. Now, these computer codes can take up to 3 months to run on the biggest supercomputer you can get, so you can't run them a lot of times. So a lot of the work is about reducing the computation you need to do, and one of the ways to do that is to use surrogate models, whether those are polynomial approximations or Gaussian processes or reduced order models, some surrogate, some simpler version of the model that's fast to run. Multi-level, multi-scale, and multi-fidelity methods, where we have our complex model here that's very high precision but has a very fine grid we solve on, and we use simpler versions where we reduce the size of that grid or we reduce the fidelity of the model, and we use hierarchies of those models in a multi-level way. Dimension reduction methods, where we take some high-dimensional problem which is hard to solve and we try to reduce it to a lower dimensional problem that approximately solves the same problem. Inverse methods, which I talked about earlier, where we have some data and we feed back into the model information from that data to try to estimate parameters or to reduce uncertainty. And the final one we said we were going to do were careful and fair comparisons. I'll come back to careful and fair comparisons in a minute. Now, today's talks match reasonably well to those themes. So Max is going to talk about surrogate modeling. Dave Woods is going to talk about design. I think we didn't quite appreciate how important design was going to be when we wrote the proposal. Aretha's going to talk about inverse problems, and Rich Wilkinson about multi-level and multi-fidelity. We don't have a talk about dimension reduction, but we could have had. But why are there no careful and fair comparisons? One of our original themes said we're going to produce these careful and fair comparisons. Now, I think the fact that we are careful meant we very quickly realized we couldn't do fair comparisons. In fact, we couldn't do unfair comparisons because we don't actually solve the same problem. We solve complementary, slightly different problems that from the outside look very similar, but because of the different methods we use, we have different ways to solve different problems. And a lot of the time we've spent here has been understanding these different approaches and methods and working out the differences between them rather than some head-to-head careful and fair comparison, or even uncareful and unfair comparisons. So some of those differences, the applied maths numerical analysis approach uses intimate knowledge of the form of the PDE. Really gets into the mathematics of what that partial differential equation looks like to produce bounds on the error. So you get a bound. The error lies somewhere between this point and this point, and if you have enough computational time and a clever enough method, which they do have, you can get that bound down to the irreducible computational error, and therefore it's gone away. You're actually solving that to the accuracy that the original equations could be solved to. Now, as I said, I'm a statistician. We take a very different approach. We treat the model as a black box. We don't do a careful analysis of what's going on inside it. Sometimes the models we deal with are too complex to do that. If you've done a climate model, you could write down all the PDEs, but it's probably 3 or 4 pages. And then we fit some random function to the output of that model, and we use that to produce a distribution for the error, so we get a probability distribution of error rather than a simple bound. Those are very difficult to compare. But we are working on it because it's a really interesting problem, and it's particularly an interesting problem if you want to chain models together. And you might have one model where we use these applied maths methods because that's clearly what you should do. We want to feed that error into a statistical approach, and we need to somehow get from those bounds to some sort of distribution. And that's one of the things that I've learned from the program. I thought I'd finish with a few personal reflections from my appreciation of the program. It's been great fun. I've had a great time. I hope everyone else has had a great time. I don't know. They seem to have had. And we've still got 2 weeks to go. This isn't actually the end of it. We've got 2 weeks to go. We've got new people turning up next week, so we may yet have that huge breakthrough, or another huge breakthrough. I've got very interested in the idea of treating models not as black boxes. As statisticians, we treat models as black boxes. We just say we don't know anything about them. We're going to discover by running them a few times and fit this random function. But can we do something by treating models as grey boxes, where we know what the structure of the underlying PDE is approximately, and can that inform us on the sort of statistical model we should be fitting? Can we use approximation theory to get an initial mean estimate that we put our random function on top of? And that involves combining the best bits of each approach. So it's not about careful and fair comparisons. I think it's about careful choosing which are the best bits and building new methods that combine those together. And we've made some progress towards that. A lot of the time has been understanding rather than building new methods, because you can't build the new methods until you understand what's going on. And I think the talks, more detailed talks you're going to get during the day, will bring that out to a greater or lesser degree. I haven't seen them, so I can't actually say. Right, I shall stop there.
Thanks very much. I think we need to